Hi everyone, and welcome to today's Chemistry Daily Booster. This is number 7 in our Chemistry Paper 2 series, and it's not actually on the advanced information. That doesn't mean there won't be questions on it, as we are aware from our earlier paper. What we're going to be doing then is having a look at some of these instrumental methods of analysis. First thing, what on earth do we mean by instrumental methods of analysis? Well, basically, what we're doing here is using machines to carry out analysis on a substance. And there are some pretty significant advantages to doing this. Firstly, they're very accurate, so they've got this high degree of accuracy. Secondly, they're very fast and can run 24 hours a day, 7 days a week. And thirdly, they're very sensitive, so they can analyse really small amounts of a sample. And that's incredibly useful if we're talking about very expensive samples or things that are very difficult to obtain. I would suggest you learn at least 2 of those advantages. Let's take a look at our first instrumental method of analysis then, which is gas chromatography. This is something we've already looked at going back to our first chemistry paper in C2, the separating techniques section. Quick recap on how it works then. In our cylinder, we've got our carrier gas, which is an unreacted gas. That is the mobile phase, the bit that's going to move. We inject our sample into the machine here, and then as it moves through, due to the carrier gas pushing it through, this little coil here is filled with particles of the stationary phase, which tends to be silica or alumina powder. Different sized particles are going to find it easier to get through this than others. So the smaller the particle, the easier it is to get through the stationary phase, and then they'll be picked up by the detector here as they emerge from the other side. That then gives us a little picture on our computer screen called a chromatogram, and we will see peaks wherever there is a substance. So here's our chromatogram, and what this is doing is it's showing us the different substances in a mixture. Each of these peaks represents a different substance, and the height of the peak shows us how much of it was present. So what we can see from this is we've got 1, 2, 3, 4, 5, 6 different substances in our sample, and substance F was in the greatest quantity because it's the highest peak. Key things here then. As we said, each peak is a different substance. And if you want to work out exactly how much of the substance there is, it's the area under the peak. Now, what we actually find is the reason we get all those individual peaks for the different substances is because they each have their own what we call retention time. That's just how long it takes for that substance to travel through the chromatography column. So what we find is those ones that are the smallest substances are going to travel through it the quickest. Larger substances are going to take longer to get through, so they have a longer retention time. Second technique, mass spectrometry. When we're talking about a mass spectrometer, this is something that's going to measure the masses of atoms and molecules. So we can use our mass spec to analyse the relative amounts of different isotopes and to analyse the structure of different molecules. The way this works then is as our sample enters the mass spectrometer, then it becomes ionised to form these things called molecular ions. Basically, molecules that have a charge on them. As those molecular ions gain energy, then they can fragment, so they can break up into smaller pieces. Once those ions pass through the machine, our little detector records the amount of each fragment. So this is what we get. This is our little mass spectrometer readout, if you like. Now, what we can see first of all, and this is probably, if you only remember one thing about mass spec, this is the thing to remember. Whichever peak is on the furthest right of your mass spec, that is the molecular ion peak. The molecular ion peak is literally the whole thing. So that is the whole molecule. And if you actually read off on your x-axis here what the mass to charge ratio is, that gives you the actual relative formula mass of the whole molecule. So in this case, it looks like it's about 58. So we would know that our mass is 58 for that particular molecule. All the other ones that we can see towards the left, these are where that one molecule has been broken up into smaller parts, and each peak represents a different fragment. The actual size of that peak tells us the relative amount of it. So the taller it is, the greater the amount present. What we can do is piece together from all of this information the structure of it, because we know the total mass of the actual chemical there, 58. We know that we're going to have these different fragments. So there's one that's got to add up to 30, another one looks like it adds up to about 28, another one adds up to 40, etc. And since we know the atomic masses, we could start to piece together what those different bits of the molecule are. And then you just build up the structure, really. Obviously, if there are bits you'd like to look at in more detail from today's Daily Booster, then do head on over to our C4 playlist where you can find the main video. Do have a little look in your revision guides, your classwork notes, and also have a flick through some of those old exam papers to find example questions. You'll see that molecular ion peak is the kind of recurring theme, if you like. And of course, don't forget to join us again tomorrow for our next Chemistry Daily Booster.